So, just gonna be honest with y'all, we're not gonna be able to get through every single problem on this review, but it seems to me that a lot of these are already on the test, or on the homeworks.
How many questions are there total?
On this particular thing, I think there's like 20, oh my god, I'm losing my place here. The other thing.
Around 20.
20, 25, something like that.
Just trying to
But he just dropped, I'm assuming that this review is very similar to the test. And there was 20, there was 25 on this. He dropped 2 of them.
But he said he was
Replace them with limits. Okay, so you're looking at 25 questions. Okay. All right, so here we go. Calculate the following limit using the factorization formula. X to the n minus a to the n can be factored into x minus a. So you just yank an x minus a out, and then this nice long factorization expression, x to the n minus 1. So for instance, if this was x to the 8th minus a to the 8th, we could write it as x to the 7th plus x to the 6th times a plus x to the 5th times a squared, all the way down, the power of x decreasing, the power of a increasing, until finally a has usurped x as the absolute sole power in the expression universe there. So maybe an example would be helpful. X to the 8th minus a to the 8th can be factored like so. X minus a times, this is n minus 1, so x to the 7th plus x to the 6th times a plus x to the 5th times a squared. You can see a is rising, x, his brain is beginning to crumble here. X to the 4th, a cubed, plus x to the 3rd. A to the 4th has taken power, but he's not, but still a little bit of a fight there. X squared, a to the 5th, x, a to the 6th, plus a to the 7th. X is gone. Okay, so there's the story of factorization of those. So here we have limit of x to the 4th minus 256 divided by x minus 4. We want to evaluate this limit, possibly using that as an intermediate step here. So I'm going to write this as the limit. And I'm going to do this now. What the heck? 256, that's not, well, what is that?
Oh, you should make it to the power of 4.
I should. So what is the 4th root of 256? What times what times what times what equals 256?
It's 4 to the 4th.
4 to the 4th. So that's x to the 4th minus 4 to the 4th. Okay. So I'm going to factor that out as x minus 4 times x cubed plus x squared times 4 plus x times 4 squared plus 4 cubed. So you can see the powers of x decreasing, x to the 3rd, x to the squared, x to the 1st, x to 0, it's dead, and the power of 4 increasing. A la the formula. All over x minus 4. This is the limit as x approaches 4. Those two cancel, and then we can utilize direct substitution as a way of solving this. Plug in 4, we have 4 cubed plus 4 squared times 4 plus cubed plus 4 squared times 4 plus 4 times 4 squared plus 4 cubed. And you plug that in the calculator to get the answer. Direct substitution, I know you know how to do that. Now you know how to use factorization formula. You good on that one now, Emily?
Yes.
All right. 15. Use the precise definition of limit to prove the following limit. Specify a relationship between epsilon delta. No more.
No.
Good thing too. Excuse me. use analytical methods and or graphing utility to identify the vertical asymptotes, if any, of the following function. So, g of theta is tangent of pi theta over 32. So the vertical asymptotes appear here, here, here. Okay, that's kind of weird. I don't know if I'm going to be able to use a calculator to be able to figure this one out right away. Maybe, I don't know. When I look at tangent, I think about what does the tangent graph look like. Y'all learned about tangent in pre-cal, right? Anybody know what the tangent graph looks like? Let's go with graph.
It's like the squiggly line, like the.
Yeah, it's kind of like goes kind of like that. Let's go ahead and graph good old tangent and see what that looks like. Tangent x. You want to make sure your calculator's in radian mode. And it continues on like that. So you just want to do tangent x and then go to mode and make sure you're in radian mode. You guys anything like that? Yeah, that's what I got. You want to make sure if your graph's all wonky, you hit zoom and then you go down to zoom standard. That'll kind of. How's that working for you, Roger? There we go. Yep. Okay. Now the question is, on this original tangent graph, where are the asymptotes? Anybody remember off the top of their head, Emily?
Pi over 2.
Yeah, not sure. Yeah, like, yeah, not sure exactly. It lies in the fact that tangent is equal to sine x over cosine x, and the asymptotes are where the denominator is equal to 0. That is, it's when cosine equals 0. Because when it equals 0, it's undefined, and that's the only locations that it's undefined. So the asymptotes are when cosine x equals 0. All right. Well, when does cosine equal to 0? I'm going to draw that one. We can do for memory pretty quickly. We know that the cosine graph starts high, ends high, and the middle is low. I know y'all remember how to do the cosine graph for memory. So we had 2 pi over right there, pi over in the middle. Cosine crosses at pi over 2 and 3 pi over 2. That's when the cosine graph is 0. And so that is when the tangent graph has its asymptotes. Pi over 2, 3 pi over 2, and so on. So, pi over 2, 3 pi over 2. It's going to have another one at 5 pi over 2. Those are the locations. So, if you think about those occurrences, so there's an asymptote at pi over 2, so it's 1 pi over 2, 3 pi over 2, 5 pi over 2. Well, it definitely looks like, this says, I'm going to jump ahead here. This one says function has no vertical asymptote. No, that's not right. This one says now, this particular graph has pi and a theta and 32, so we got all kinds of other stuff being multiplied there. It looks to me like, but I'm just focusing on tangent theta. Pi over 2, 3 pi over 2, 5 pi over 2. It's at those where that's going to be 1, 3, 5, 7. So all those numbers is where the asymptote is. So I would say that's sort of like k pi over 2, where k is 1, 3, 5, 7. So it looks like where k is odd. See if everybody's with me on this one so far. Everybody good? You guys good? So pi over 2, 3 pi over 2, 5 pi over 2. So you see 1, 3, 5. Those are odd numbers. So we can write that as k times pi over 2, where k is an odd number. K is 1 or 3 or 5 or something like that. Another way that you could do that is you could say, just think about these numbers, 1 plus 3 plus 5. That's the same thing as saying 1 plus 0 1 plus 2, 1 plus 4, 7 is 1 plus 6. Okay? This is such a weird layout. 1, 3, 5, 7 can be written as 1 plus 0, 1 plus 2, 1 plus 4, 1 plus 6, 9, you can think of as 1 plus 8. Alright? So these numbers up here are all k, where k are all the odd numbers. Another way of writing that is saying 1 plus, I notice 0, 2, 4, 6, 8, those are all the even numbers, okay? Or I could say the same thing saying 1 plus 2k, where here k is 0. I can say 1 plus 2k, where k is equal to 1. 1 plus 2k, where k is equal to 2. This is 1 plus 2k, where k is equal to 3. This is 1 plus 2k, where k is equal to 4. I don't know why they're expecting it to be some stuff, but I'll walk you through it anyway. Alright, so you can see k is 0, 1, 2, 3, 4. So the way you can get those odd numbers is by saying 1 plus 2k, where k is an integer. So now I don't have to actually say odd and rely on the person to know what's even and what's odd. Well, it doesn't matter. Every odd number is 1 plus 2 times k, where k is any integer. That's beginning to look a little bit closer here. So when what they're saying, what I found is that there's asymptotes on tangent theta at pi over 2, 3 pi over 2, 5 pi over 2. Another way I could write that is 1 plus 2k times pi over 2, where this is a way of writing that odd number. Are you with me so far? Okay. I'm just going to hit the pause button on this and say this is a great situation where freshman year math and science students get really frustrated at their high school teachers because their high school teachers didn't teach them all this stuff. Then teach them all the background stuff about how the heck do you have this 1 plus 2k business? What the world is going on here? And there's part of it where, yeah, it is our fault. There's also part of it is we can't teach you everything, and you got to kind of trace it out, figure out what's going on. But you got me here to help you right now, so that's okay. 1 plus 2k is another way of saying it's an odd number. So we say there's an asymptote every 1 plus 2k times 5 or 2. Now, in this particular problem, we are multiplying this. We don't just have theta on the inside by itself. We have pi times theta divided by 32. So we would have, in our situation, we have tangent of pi times theta over 32. So I should, to clarify this, the original one, tangent theta is asymptotes when theta equals, that is what's inside the parentheses is pi over 2, 3 pi over 2, 5 pi over 2. So in our situation, we're going to have asymptotes when the stuff inside here, pi times theta divided by 32 equals pi over 2, or 3 pi over 2, or 5 pi over 2. Okay? When all this stuff in here equals those asymptote values. So in other words, that's whenever pi times theta divided by 32 equals this formula right here, 1 plus 2k times pi over 2. And that's the formula that we have to manipulate now. Because they say occur when x or when theta or whatever it is. I guess I could put x right there. I'm using x and theta somewhat interchangeably. So anyway, all right, now here's our formula. What we're going to do is we're going to divide pi from both sides and multiply both sides by 32. So the pi's would cancel. Multiply both sides by 32, I get x equals 1 plus 2k, and then 32 divided by 2 is 16. And so that's going to be x equals 16 plus 32k, where k is an integer. Is that one of the answers?
Yeah.
Answer A?
Yes.
All right. Let's make sure we're right. The answer is A. I guess I probably should check that before we did all the work. That's all right. Emily, any questions?
No.
As a general, I guess the things to remember on this one, remember how to figure out where the asymptotes are. I could see a very similar problem, but with just something slightly different inside here. In that, on your test, I don't know. I have no idea how it can change. But some of the ways that you can do this are having, remember where those values are. And then this formula right here is a good one to have memorized for odd numbers. I had 1 plus 2k. Okay, I had to derive that through this whole process because I assume you had taught it, didn't know it because I didn't teach it in pre-cal. So that's a pretty good number. What if it was evens?
Would it just be 2k?
Yeah, it'd just be 2k, where k is an integer. That might be a good formula. I could see there being a change. I could say that having cotangent rather than tangent on the test, because that would be a sufficient difference. And the difference between tangent and cotangent is cotangent, the graph looks a little bit different. It looks kind of like this. And its asymptotes are wherever the sign equals 0. And if you remember,
Would it be even in that case?
0, pi,
Yeah.
2 pi. So yeah, actually it's not even the evens, it's actually just every k pi
Oh.
are the asymptotes. Here it's at 0 pi, 1 pi, 2 pi, 3 pi. So the asymptotes on cotangent of x occur k pi, where k is an integer. So, very quickly, we can apply this. What if I had cotangent of 3 pi x over 15? Well, the asymptotes there are going to occur whenever 3 pi x over 15, I shouldn't choose 15, 3 or 15 cancels, we'll say over 17, equals k pi, whenever it equals those values, 0 pi, or 1 pi, or 2 pi, or 3 pi. And so you would just divide both sides by pi, multiply both sides by 17, divide by 3, so you'd have 17k over 3. It's a lot, I mean, that's a ton faster.
And that would be the answer.
That would be the answer for a cotangent, yeah.
Okay, where any integer that is k.
Yeah, yes, exactly, where k is integer. K is int.
Okay.
It gets a lot faster once you get through this
Yeah.
little 1 plus 2k, that's how you get odd numbers, and it's weird for tangent. But yeah, you can see this, you can do this in almost less than a minute.
Yes.
If you've got to remember what cotangent, where the asymptotes are on tangent and cotangent. But if you can't remember that, then you just remember the tangent, sine over cosine, you graph the cosine graph, you know it's where it's pi over, figure out where it's 0, and for cotangent, it's cosine over sine. If you draw that graph, you know that the asymptotes are gonna appear wherever that one's 0. Okay, I spent too much time or enough time on that one. Let's move. This one says find the following limit or state that it doesn't exist.
Just plug in the number, put it in.
You think so? You think we just do a plug it in? Let's find out. So this says the limit of 5 over square root of 25 plus 3h plus 7 evaluated as h approaches 0. So let's plug it in first to see what happens. You always want to do that on these limit problems. Square root 25 plus 3 times 0 plus 7. So it's going to be 5 over
Square root of 25.
square root of 25 plus
7.
7. So that's 5 over
12.
5 plus 7, 12. 5
that's
over
the
12.
answer.
There you go. Always try direct substitution if you can. It works every time except when it doesn't. Use the following definitions to prove that the limit of square root of x equals 0 as x approaches 0 from the right. Assume, yeah, this is the other one. Look at this. It's probably like that homework you were talking about, where it's got multiple parts. You've got to assume f of x minus l, and you got to fill in the blanks. You have homework like that? It's the whole epsilon delta one.
That one.
Yeah, it's actually pretty nice that they kind of give you all the steps all the way through. For the most part, yeah. What he said yesterday was great. Epsilon delta is more applicable in Calc 2 and in the higher maths. At some points it's the formal definition of limit. Let's deal with these guys. Maybe we'll finish. Evaluate the following limit. The limit of this as x approaches infinity. Okay, ooh, so we can see who wins, right? Numerator, denominator? Maybe? Okay. Well, what I might want to do first off is split this up into 4 limit problems. The limit as x approaches infinity of 4 plus the limit as x approaches infinity of 168 over x plus the limit as x approaches infinity of sine squared of x cubed over x squared. Now this part right here we can handle. The limit is of 4 as x approaches infinity. So this
It's
is
4.
It's 4. It's always 4, 4, 4, 4, 4. No matter how big or small x is, this function is always 4. So that takes care of that. What about this one? As x approaches infinity, we've got 168 over a larger and larger and larger
So
number.
denominator wins.
Denominator wins, so that's going to be 0. Hooray! I'm liking this problem. Until I get to this part, the limit of sine squared of x cubed over x squared.
That means the numerator wins. I mean, the numerator would win because it has x cubed.
Yes.
Yeah.
However, that formula, sort of thing that we observed, happens only when you have polynomial over polynomial.
Okay.
you know, so, like if you just had an x cubed over x squared, then we would say that the numerator would win. And so you might say, my thought at this point would be, what are the values of sine? What are the values of sine? Anybody know? What type of number, like if you say, you know, sine of 50 or sine of whatever, what sort of values you're going to get? You all know the range on the sine function? Nope, not top of your head. Let me draw a graph for you.
It's always the two.
It's going up and down like this. It never goes higher, never goes lower than these boundaries.
Oh, the range is one, isn't it? And negative one?
Yeah, between -1 and +1. It doesn't matter how large or how small x gets. Yep, it's always going to be between those two. So what about sine squared? What does that look like? Sine squared of x. Well, that just means sine times sine. Alright? So everything that's positive is going to stay positive. So you have like a half, so it's going to look like that up until 1. And everything that's negative, what's negative times a negative? Positive. So it's going to kind of go like this. See what I'm saying? Let's graph it on a calculator. Just graph sine squared of x. Which, okay, the way that you type that into your calculator is sine of x, and the parentheses around that whole sucker squared. Parentheses, sine x. Got to close. They're throwing a parentheses around that right there. Squared. Graph. Hippity hoppity. There we go. Hey, okay, so that's great. This isn't. So this looks like it's stuck between 0 and 1, right? Okay. But this guy up here is, or the denominator, is going to get really large. Okay? So we're going to have like 0.5 divided by like 1,000,000. See what I'm saying?
Should be 0.
Maybe. I'm a little sketchy on what's going to happen as it gets closer to 0. Like, what if this was like a really small number? Like, what if it was like 0.0003 divided by 100,000? 0.0003 divided by 100,000. That's a really small number. I got like 3 to the negative 9.
Yes, so it's approaching 0.
I think it definitely is approaching 0.
So the answer would be 4.
Which makes me think the answer is 4. I don't know. It almost seems too easy. Let's see if we're right. No, we're right. So, I mean, yes, we're right. So, yeah, you might have thought because that x cubed is in the numerator, it's going to win this approach infinity. It doesn't. Or in which case you would have thought the limit doesn't exist. But you got to think about what sine squared is. Okay. Let E be an even function and O be an odd function. Determine the symmetry, if any, of the following function. Was this in your textbook? Even and odd? Even plus odd. Off the top of my head, I don't know the answer to this.
Couldn't we do like an example on the calculator?
Possibly. I can tell you some things about even functions. Even functions mean that f of negative x is equal to x. If f, I should put some other numbers. If f of a equals b, then f of negative a still equals b. So like f of 1 is 2, and f of 2 is 3, and f of 3 is 9, or something the negative values are still having those same y values. An even function looks like an x squared, where it's matched on either side, like a quadratic or a polynomial with a power 2, like an even power. An odd function, if f of a equals b, then f of negative a equals negative f of equals negative b. So like you have 1, 1, 2, 4, 3, 9, you'd have negative 1, negative 1, negative 2, negative 4, negative 3, negative 9. It looks kind of like that.
So X cubed.
Yeah, like x cubed. Hence the name even and odd. So if you take an even function and add onto it an odd function, so I'm like taking like these values and adding these values to it, well that's just going to be something even more up here in the first quadrant. I'm taking these values that are in the second quadrant and I'm adding those which are in the third quadrant, and it's kind of pulling it down. It's kind of funky. I'm thinking like, I don't know, it's certainly not going to be even, okay? It's certainly not going to be symmetric across the y-axis. That one's out. There's not going to be symmetry across the x-axis because it's a function. You're not going to have the same stuff up here as you are down there. So that's out. It's possible we would have symmetry about the origin or no symmetry.
It's symmetry about the origin.
The odd function does have symmetry about the origin. The even one has symmetry around the y-axis. According to this, and the answer here, no symmetry.
Really?
Yeah. It might be that this is not the best of examples or whatever. It might kind of look like it does. You've got x squared plus x cubed.
Yeah.
Maybe in the region between 0 and 10 it kind of does look like it, but maybe farther out it becomes odd. It's like maybe it's close enough here that it looks kind of the same, but if you zoom out, it's not going to be that. Here, I'll tell you what the easiest way we could figure it out. I mean, if it's x squared plus x cubed, and we plug in, let's plug in something rather large. What about 100 and negative 100? So 100 squared plus 100 cubed. Yes. Sure.
Do I need to pass?
Nah, it's good. 100 squared plus 100 cubed. 101 plus 4 zeros. And if you plug in negative 100 squared plus negative 100 cubed. Well, it's definitely, I don't know why I'm doing this because I guess it would be, oh, okay, sure. Negative 99,000.
Okay.
If there was symmetry about the origin, then we would see that
It would have been negative.
it would have been negative 101.
Okay.
Yeah. In this case, I would memorize even plus odd, no symmetry. You need to memorize evens and stuff like that. It seems to me like this is some sort of fact or facts that might be in the textbook. You guys have access to the textbook, right?
Yes.
Yeah. Something memorized. What sort of in that chapter 1 material? I guess is that like sort of preliminary things that you need. I can't remember. I've not seen the textbook. All right. Intermediate value theorem. Use graphing. Okay. We don't have time for this. We've got. Let's glance through the rest of the test, and then we'll pick the one. Intermediate value theorem. That's possible. We can guide through that one. This one, number 22. Use the graph of f of x in the given figure to find the following values if they exist. F of 3. Okay, great. That means plug in 3. That one, there's a hole right there. Does not exist. Limit of f of x approaches 3. You can kind of see that seems to be approaching a y value of 6. F of 0 means plug in 0. There it is. the limit of f of x as x approaches 0. Well, that's looking at both sides. Yep, definitely approaching, I'm assuming that's 7 right there. Okay, so yeah, looking at the graph, state the domain. Domain on these sort of problems. You've got, this is a reminder, you can rewrite this as any time you have fractional exponents, 4 minus x squared, you could write that to the 5th power, and all of that to the 1/2 power. Because if you were to multiply the 5 times 1/2 powers. So 1/2 means square root, so that means 4 minus x squared to the 5th inside that square root. The domain is where this sucker is positive. So you have to have 4 minus x squared to the 5th has to be greater than or equal to 0. You can take the 5th root, and 5th root of 0 is still 0, so 4 minus x squared has to be greater than or equal to 0, and you can carry that through where x has to be. So you might just want to just do this time limitations that we just are bound by. You might want to scribble something down, domain problems, especially if the this is a rational exponent problem. 24, the magnitude of electric field at a point x meters from the midpoint of this line, 0.1 meter line of charge given by this formula. Evaluate the limit, okay, of e of x as x approaches 15. Well, it seems to me that this problem right here, you're just going to try to do the direct substitution. Plug in 15, plug in 15. You're definitely not going to get 0 there. They want to round your decimal to 4 places as needed. So this is just making sure that you can apply the limit problem. And 25, determine whether the graph of the following function has symmetry about the x-axis, the y-axis, or the origin. Check your work by graphing. Well, I automatically know that this function is not going to have symmetry about the x-axis. Because if it did, then that means there'd be points down here that match these points up here, right? You have something like this. And there's no function in the world that would look like this. That's a one variable function, that is, because it failed the vertical line test. So that's something you know right off, no symmetry across the x-axis. The other stuff, if you remember, if it's symmetry across the y-axis, that means that you're looking at an even function, or more specifically, f of a equals b, then f of negative a still equals b as well. Scratch out even, and I'll say symmetry across x, sorry, the y-axis. That's right. This point over here matched this point over here. This point over here matched over there. This point over here matched over there. Symmetry across the origin is like when you have odd functions where you've got, you know, we saw a second ago, this one and that one. This one positive is equal to this one negative. And the way you do is you just plug in a number, plug in, you know, f of 5 and see what number you get. Then plug in f of negative 5 and see, do you get negative of that same number? If you do, then you're looking at an odd function and you have symmetry around the origin. Okay? So yeah, let's go back and talk very quickly about the intermediate value theorem. Since it looks like there's going to be at least one question on that. The intermediate value theorem states, first off, the condition of the intermediate value theorem is that it's continuous. Okay, so you can know automatically that it says if the function is continuous on the interval. Okay. Yeah. So and L is a number, whatever, then f of A and f of B. Then there's a number C satisfy the case. Let me tell you a little story. I can't remember how we taught this one, but I'll tell you how I teach the intermediate value theorem. All right. a long time ago, I was, 3 feet tall. Now, I am 6 feet tall. Okay? My growth is continuous. Alright? At least during that time period when I was growing. I was constantly growing. It never like jumped. It wasn't like one day I was like 5 feet, and the next, very next moment in time, I was like 5 feet 2 inches. I mean, it was a continuous process. Okay? So, since at some point way back when I was 3 feet, and now I'm at 6 feet, doesn't it make sense that there must have been a time between 20 years ago, so we'll say 20 years ago would be 1998, and today, that I was 5 feet tall? Doesn't it make sense? Assuming that it's a continuous function with no jumps, no gaps, no asymptotes and stuff like that, doesn't it make sense that if I pick a number here, any number here on the y-axis between 3 and 6, that there's got to be somewhere, I don't know where it is, but there's got to be something intermediate value that's going to match it. Seems to make sense. There must have been some time when I was 5 feet tall. That's what the intermediate value theorem says. So I look at the y values and I say for any value between these two guys, there must be an x value where that occurred. And there may have been multiple x values. I could have, the function could look like this. It doesn't. It looks like this. But the catch is the function's got to be continuous. And if you're saying between these two y values, picking any value there, you've got to have an x value between this one and this one. I can't say anything for sure about the time before or the time afterwards. But during that time period right there, if I know that 3 is matched with A and 6 was matched with B, then I can say any value in between here and here corresponds to at least one occurrence somewhere here. Maybe that'll help make that a little more sense. All right. Good luck on Friday. We'll be in here the whole time. Bring your math book. Fully charged. There you go. Hang on.